Okay, good morning. It is interesting how offline attendance is always much lower on Fridays than on Thursdays. Well, it's nice to have you here. So I think the sound is a bit strong, but I cannot change it. So today we will start, well, we will try to complete the vertical parts of the envelope with the curtain walls, which is a very specific case study or specific area of envelope. So next week we can go into roofs, right? The cover is the same building we saw yesterday. This is the visitor center of Yoshio Taniguchi. Very elegant, simple building. So we have our following assignment. It will be a bit shorter. So the idea is to submit it next week, right? So the idea, well, you're already very familiar with this detail. We don't need to be sophisticated, but we have to make, or you should make your own section detail, right? And the condition is to use just steel profiles, standard profiles, only L tube and plates. Should be standard, so you can find any catalog. And the point is to achieve water protection, right? But you don't need to have a thermal performance. Think this is kind of greenhouse or veranda windows, so heat is not a problem, but you have to keep water out and wind reasonably. So you will work with just one single glazing of 6 millimeters. And you have to find also how to fix that glazing and how to be it replaced. Okay, you can weld, you can screw, you can choose whichever, you can use both, right? So it's just to design that section of the window with as this like a frame and with a sash and with the glass, right? Those two elements. And of course, how you plan to fix it to the fabric, right? In this case, to the spandrel of the facade. So still, just to give you an idea, for this kind of small elements, we use about 2 millimeters thick, right? Can be a bit less, 1.5, but will be a bit weak, depending on the elements. Can go to 3, but much thicker will make the things too heavy. So it has to be as simple as possible. So it has to have the minimum of elements, right? And to be as light as possible, right? Because the steel is very heavy. You don't need to worry about hardware and so on, just this section. Okay, so you can use A4, A3, probably one A4 is enough for this detail. And should work at a scale 1:1 or 1:2, because real size is like really fitting the sheet. So you have to describe the elements and so on. So submission will be next Thursday, right? By the end of the class, more or less. No, by the end of the day, actually. Well, I forgot to change this, but it's already there. So Thursday by the end of the day, so we can collect. This wasn't for the online, right? So actually, this is Thursday, and online you can do by. Right. So at this time, the submission is flexible. If you submit on time, you have detailed feedback. If there's something to comment, you can submit until 1 week later, or even later. But in that case, you will have grading, not feedback, because I cannot keep writing on assignments forever and ever. So I have to do it in one go, right? So you can submit Thursday. Of course, Friday will be okay also, right? Because if you can submit online till night, you can submit Friday morning here. But the earlier you submit, the better. Any question? Well, if you have questions, please ask, but don't ask Wednesday night, because for the previous assignments, all questions came like the 1 or 2 days before the submission. That's kind of discouraging. You don't need to spend the whole week doing the assignment, but it is good you become familiar with it as soon as possible. So you think about it, you get your information, you can elaborate last hour, last minute, whatever, but you at least have 1 week thinking about it and understanding it, right? Okay. Let's go with the lecture. We're into the third chapter. In the photo is one of the elegant curtain walls here in Seoul. This is a SK building in Uljiro, Chongno, by Kim Jong-sun, SAC Architects. And this one is the famous Seagram building. So you can see from close by how bronze after 60 somewhat years looks, right? So bronze is getting old, but it is aging quite well. And this is the plan. Let's see if we can go to the end of the lecture. So this is mostly repetition of construction materials, so I will not detail much, but actually the concept of a full glass enclosure is quite old. It's kind of very old challenge in terms of technology and intentions. Paxton Crystal Palace was the first totally glass building, actually it's roof and envelope, and still amazing building, right? Probably the first thing which looks like a curtain wall is Walter Gropius. It's 1913, right? It's like of the earliest examples. It's one of the best. But the development of the technology was in the 50s, right? It is after the World War when the large glass is available industrially and is more available, more cheap. And when the curtain wall concept was developed, and was like a 2 steps, right? Well, you can find more, but I chose the ones I think most interesting. We have Mies van der Rohe, 1951. 1951 was already quite old guy, and again Jean Prouvé in France, in Lille, right? The same year, and I call it false curtain wall because the structure has not that intermediate element. The curtain wall is stuck to the structure directly, right? So the concept is a little bit primitive or more simple, right? It's not really. And then the real curtain walls, again, Jean Prouvé wins the prize, the first one, 1955. One of the most beautiful, best curtain walls ever. Then second one is Ponti and Nervi in Milano. Those guys which are already familiar with us, and Mies van der Rohe right after, but he was after, right, in New York, the famous Seagram. So let's spend a few minutes with them because that helps us understand the problems they had and how we came to the curtain walls we build today. So, well, you know, 1951 is the first large work of Mies van der Rohe in the States. And apart from the very simple gesture of putting 2 towers rotated side by side, so they will have all the 4 sides free with you, which is very silly, but nobody did before, right? And the skeleton, the other innovation here was the full glass facade, right? And we have interesting photos from the construction. And you see that's like a 2-floor set, full span between columns, right? Prepared in the workshop and assembled just on one go, right? And you see there's one piece which fits perfectly in the structure, right? You see that you have the crane and you need just 2 people on the top and probably 1 or 2 on the bottom just to fix it. So it's incredibly fast, efficient, and safe to do because you work from the inside of the building. This is the construction on the top. And it's the finished building, right? This is like an old original photo. Those buildings were repaired recently, right? Then Jean Prouvé, this is, I couldn't find much better photos. You can look at the book of the complete works in the library, in the science library. But this has two interesting concepts. First is the exoskeleton, right? The structure is outside. And then a facade, not of glass, but totally of light metal panels, prefabricated, that is screwed, put in place with screws, right? And all elements are very light, industrially made, which could be standardized to make any kind of structure, right? This is in France, and I think the building still exists. Now we come to the real curtain walls. And 1955 is the Nobel Tower. If you see the elevation, this is like a standard expensive curtain wall nowadays, right? So that tells how much he did in the right direction, his idea, right? In terms of proportion, in terms of logic, in terms of design, construction, and everything. The photo is from a recent renovation. So those buildings need some kind of repair. And the comment by the architects was that it was so logical, so easy to work with it, right? That the renovation was really, really fast. See the round corner. We'll see later that corners are one of the critical points in curtain walls. And Nouvel, or just, sorry, Prouvé solved it, but just rotating and having this more or less the same solution in all sides, right? And this is the detail. This is not only simple. This is the horizontal section, and this is the photo of the mullion. It is beautiful, right? It's a piece of art. This mullion actually was he made a patent. This is like a probably extruded aluminum. And he would have different sizes depending on the needs of strength, right? But see the simplicity of the element being able to hold solid panels or to hold glass. And the way to fix it, or to fix the elements to this mullion, right? You have the main mullion, right? You have an element you put from the inside and you press it with a bolt. But whatever you press in between has a neoprene elastic element. So both glass or solid panels are taken just by pressure with elastic element. So there's not any problem about adjustment, differential movements, thermal movements, or whatever. It's simple, practical, extremely easy to assemble, safe, has all the conditions, right? And you have the full patent with all the possibilities. And well, it didn't become generally used. I don't know why, but it was quite logical. Then we have Seagram. Also, it was after Milano. I put it before because it is much more easy to understand, right? Very elegant. And you see the modulation is very similar to because you have the basic needs of the spandrel, the suspended ceilings, so this measure, and you have also the limitations of glass and the mechanical loads, right? So probably this has to do with the technology of glass at the time, and also some kind of preference for specific proportions. I bring this photo because the Seagram is this detail. I couldn't find better ones, but if we have Chicago, New York, and then Toronto 10 years later, and Chicago a bit later, you can see that the simplicity of a Seagram became more and more complex as the technical demands increased. And that was one of the weak points of Mies van der Rohe approach, which was great when you don't worry about thermal loss, right? But it has to deal with very extreme climate and very harsh conditions. Things become extremely complex. But going to New York, we don't have the exact detail, but we have this section, right? You have the basic structure, and Mies van der Rohe basically worked with one element fixed to the structure and a second element fixed to the first one. And then here is where he put the mullions of the curtain wall, right? Okay, two intermediate elements which allow for all kinds of adjustments. This became more or less the standard today because it is easy to apply. You can work from the inside. Again, it's quite safe. This is the heating element. Right? You don't need to worry about it now. So it is more or less what we use today with the small variations. Chicago was much more sophisticated, but it was like too much. And the complexity brings some cost. And we try to simplify in general. So, well, this is, I could have worked here, right? So you can see more clearly one first element connected to the structure and the second element connected to the first one, which again connects to the mullions, right? This will allow for all the fine-tuning adjustments. And you have very soft connection with the structure, so they can have some kind of movement independence, some kind of flexibility there. Perlugineri and Ponti, again, fantastic pair of architect and engineer. Again, see that in terms of proportion and aspect is not surprising today. It's a bit different than the idea of Mies and Nervi, right? They stress more the windows, and they're a bit softer with the spandrel space, which makes sense in terms of light and heat control, right, in some aspect. This is a closer by look. Again, you see this has a different aspect, but still is a curtain wall we see nowadays very often. And I collected, this is my school notes from 1983. As there was when I was annotating, and I redrew, and my notes tell, well, this is before Seagram. It is very advanced technology, and they were inventing this super sophisticated. This is what I annotated, right? How does it work? Well, basically, it's the same idea of Mies van der Rohe. So I have to go through the bits. This is the slab, and that's kind of a steel railing over which you have freedom to put anywhere the next element. So you have much freedom to find the right spot in one of the axes. Then there's like those two angles, which are cast aluminum, which would be those holes connected to this railing, right? So they would have kind of this kind of a space which would hold the following piece, which is a kind of bolt, right? And if we see the detail of those angles, they have some kind of tooth. So you can regulate in the other direction in depth. And once you put in the exact point, it will not move, right? So this is the detail of that part over there. And then this passing bolt, this will be the top view, will hold also made to order neoprene element, which would be enclosed between those two, right? And then on this neoprene is kind of very strong H element, it's shaped, to which the element which fixes the mullions is connected. How do you achieve with this? So this is the detail of that H. So you have one element that's a passing bolt, which is tightly connected to the structure. And one very strong element, which is tightly connected to the mullions. But in between, you have pretty elastic element in one point, which will allow rotation, thermal movement, structural movements, and will absorb sound, right? Because it will damp the vibrations. No Nouvel, well, Nouvel kind of did in between, right? But this Nouvel did between the mullion and the panels, but this makes the whole curtain wall in the building go back. The whole curtain wall is floating from the facade, right? Not a single point is tightly fixed. So this is the top view of that bolt, the comb and the elements taking the emulsions, right? The emulsions in the top, and the possibility to have adjustment exact in all three axes, but always having an elastic thing. This is an additional element. You never will see that. We already fixed to that kind of railing of the structure with one element, but this one point fixation. To have more rigidity, to have like a passing bolt to a more stronger element, which is also connected to this kind of structural element, right? So the element is really, really well tightly connected to the structure. This is a photo. So this building also had some repairs. Actually, at some point, one small airplane crashed against the facade and they had to repair it. And we can see how it is done. So you can recognize the angle, right? You can recognize the railing. You can see the teeth, which makes the adjustment be really fixed. The first bolt, this is the second, the stronger bolt, which connects the whole height. So you have not any possibility of rotation. So it's not one fixed point, but it's 1 point plus the whole line. You see the second bolt, which will connect to the other side, right? And we can see, let's change the color, still the element, which is connected to that rubber, which then will connect to the mullions, right? It is amazing, right? Without any experience, they thought so much and they made it. And this building, after 64 years, is having not any problem at all. I never saw this made later. Surely this is expensive, right? But it is like the perfect solution. And I think I don't know why it is not more published. It was really hard to find the information. This is why I have to go to my notes, right? That's like the perfect example. So just to start, I commented that the corner is a very difficult point in the curtain walls. So I put in your sheet a question on telling why corners are difficult in a curtain wall, right? What is the problem in the corners? And you see that Mies van der Rohe spent a lot of time designing corners. Jean Prouvé did circular, right, round. Nervi just avoided them. If you see the facade is ending in the concrete elements, so they have just two elements of curtain wall. And Mies van der Rohe had a pain working on those areas. Why? What happens with the corners? Just think. I think I give you space for 3 reasons. And this is a nice exam question. Let's have 1 minute for this. To write just 3, 4, 5 words. We will comment later, right? So don't worry, we will know the solution today. Okay. Who found at least 3 reasons? 1, 2 reasons? More people? 1 reason? At least 1? Well, that's something. We'll comment later. This is a photo of a Chung No area, right? And if we see differently from general apartments and housing, office building has like a very standard solution in curtain wall. So I think it is worth having the basics because very easily we'll find the need to work with them. So again, this general talk is what we saw in materials, but a bit more expanded, a bit more examples. This is the basic two groups, and this is my classification for the class. You may find different classifications in other books, right? It can be the full glass or the panels in which the glass is just one part of the curtain wall, right? And they can be both light or heavy. Light is the usual aluminum stainless panels. Heavy is usually reinforced concrete. And the glass curtain wall, you can have a mullion and glass, only glass. You can have plastics, and you can have even air filled like a balloons, right? Okay. If EFTE or Teflon varieties. And the details we have to work always is what we asked for the assignment the other day, but not for the curtain wall, but the structure, is the typical detail, which is what you saw in all the examples we commented, right? We have the one full floor and the connection with it. So in this way, with this section, we understand the full working of the curtain wall, right? Then you can detail larger scale that part. Then the corner, as we said, corner is special. This detail, of course, will work mostly in floor plan, will be horizontal section. The top, again, top and corner or top, always we have a specific solution. We have to deal with the roof, and there's plenty of solutions to work with it. And then if we have a special finishing in the ground, right, we have to make the low border and then what we already are familiar, the plinth. And this happens for both, I just annotated it. So you will have like at least 5 details you have to work to define more or less the curtain wall. This is the panels, and this is one example of light concrete. Light concrete is usually like a fiberglass reinforced concrete, right? Which can be very thin, quite light. And this is very common. There's many examples around town. Usually those concrete elements are done, not always, but usually in reinforced concrete structure, usually. Right? And they have just pieces, right? Like a spandrel element, structural element, and then the windows put in between. Usually it's not unified. It's like you have at least spandrel, the column, and then the window, right? And you apply them to the structure. This is the most usual. This is an example of a halfway light and heavy. You see the section. And in this case, this is steel structure, right? And this is taken from the American Details, Francis Chin construction. See the process of showing the basic detail: elevation, section, and detail, right? What they do is to have like 2 connection points, top and bottom. The book of Chin in purpose is showing concrete and steel to give you the variation of the solutions, right? But the elements are the same. So you have one element to fix on the bottom of the panel and other at the top. So you will have people both for one single panel. You have one person working on the lower floor and other person on the top floor, right? Or the ceiling to fix the thing. They have to go to one stair and work on the ceiling. You need enough space for the workers to do that. Oftentimes, I see details where you have this kind of angle totally stuck to the ceiling, and there's no way to put any kind of tool to work there. This is more the light fiberglass reinforced concrete we saw before. You see the spandrel element, the column element, and then the window, right? Okay, basically 3 elements, in this case, the corner. This is here around Seoul, and they're nice buildings. So this is quite well done, but obviously it's not a material which ages very well. It is porous, so all that dirt of the silicone and the pollution will get absorbed by the joints. There's elevation, and again, this is a different detail, the case we commented, in which the plinth has a different ideas. So you have to work both connections and then the ground. Heavy prefabrication is like a much heavier, like a really thick concrete. This is an example in Madrid, one of my Sombe. And we saw some examples, speaking of structure, but you will see very seldom in housing. For some reason, after the disaster we saw in the United Kingdom, prefabricated houses falling down, it's not too much used, but I saw some projects reviving them. You will see this mostly in industrial projects because it's very fast, cheap, it is solid, it is fireproof to some extent, so it makes a lot of sense. And you have like especially for industries, elements with some kind of ribs, which will help making it strong but light. The problem with heavy prefabrication is heavy, but we'll try to save material and weight, right, as much as we can. And very often you have sandwiches with the insulation and the finishing elements, right? And you can integrate a window, but in this case, we have to calculate the panels so the area we have in between is strong enough to support the loads they are calculated for. There's a limitation there. Interesting, we see the detail of the corner. This is one example, again from the book of Chin, which you see it has by pressure gaskets, right? Okay, gaskets, right? In this case, a mortar is a mortar which does not contract, that really gets in the shape of gaskets. And you have in 2 points, and that creates this kind of chamber exactly with the same function we saw in the windows, right? If you have any kind of leak thing, you will stop here, and then it will disappear, or you will have some weeping point and the lower point of the panels. This is interesting. Heavy panels are very heavy, very rigid. So fixation must be very strong to hold the weight. You have to go to really solid structural elements, but they will have, depending how big they are, and those panels are quite big. This is only expanded panels. They'll have a lot of movement on themselves. Since they will have the direct sunshine, right? They will heat much more than the structure, which will be more protected. So there will always a difference of movement. Same when it is very cold, or this was the sunshine, right? There's not kind of a bug there. If it is very cold, it's the same. It will contract much more than the structure because the structure is more protected. So what we do is, you don't need to go to the full detail. It's a bit complex, but usually it's one point is tightly, completely, rigidly connected to the structure, and the others will allow for some horizontal movement or some rotation, right? So you can apply them, you can adjust, so they will not move, but they will have the possibility to expand, to contract without disturbing the structure. When you have the full facade elements, usually you will connect to the structure one part and then panel to panel. You'll have panel to panel connection and panel to structure. This is another possibility, right? Because you see the structure is not in the line of the panels, right? So the panel is covering the whole expandable area. So you will connect the upper part to the structure, but the lower part to the top of the following one. And this is the structural element which is really rigid, right? Then panel to panel, you are a bit softer in the connection. And the larger the panel is, the more difficult the connection. In this case, all connections are to the structure, which is safer, but the book says it is a bit more dangerous for whatever reason. But the point is not going to the full detail. I don't think you will specialize, but it's nice to understand that heavy panels need very strong connection to the structure or to the panels with some degree of movement. That the degree of movement is the key word. If we go to light panels, it's a bit easier because then we have to deal mostly with wind. And we see the critical wind is the suction because it pulls out and sometimes the things fall. This is not very good photo, but this is one of the Jean Prouvé early buildings. Prouvé invented almost everything. And you see, this is very much the same technology we apply for the fabrication of cars. So you punch in the plate, probably aluminum, and then having a gasket. And that round shape is just to avoid corners, right? It's much easier to fabricate, and you have much more soft distribution of stresses, because obviously this area is very stressed, and you have a concentration on those points where the tension gas goes to the thinner part, right? The same principle as in cars and airplanes. You have always some margin, and those elements are much central, much more easy to put. So the most basic is the one element, totally solid or with an integrated window. Again, you put from the inside, and this case will be always connected to the structure, not panel to panel, but with the panel to structure, right? And those elements are an elaboration of what we saw with Mies van der Rohe. It's kind of standard. And this is just examples. This look at really 1950s, yeah. And you can have a system, right, in which you have all the different possibilities. And curiously, blinders on the outside, which is the right point as we commented yesterday. But of course, those early polymers and the maintenance is a problem. So it's not very successful, but still it was interesting. He thought so much in this kind of construction. This is again one of the patents of Jean Prouvé of this kind of system. So modulation is basic in this case. And the construction, you see this multi-layered, right? In this case, you have several pieces, which I don't know how he joined, probably with not screws, but something more solid. And you have some kind of ventilation elements and insulation between, right? So you have this absorption of noise, this vibration in the intermediate layers. And this would be usually between, I don't know, but nowadays it's like between 10 to 20 centimeters, depending on the insulation needs, right? And this is the one detail. Again, the side, this is a horizontal section. This is all the case of solid panels, totally filled with foam. This obviously is under 10 centimeters size, but see again the simplicity of the connections, right? You have one rubber element to which you connect one solid thing, and here you screw and you push with another element by pressure. So just the pressure pulls the element. So the let me start again here. Okay, so you screw, right, but you really make pressure, and the only contact is the rubber element. In the corner, there's not even screw, this kind of a very solid gasket, which is connected to one steel element at the end of the wall, right? Just totally by pressure. So you always have this kind of elastic joint between the panels and anything else. And you have always some space to allow for tolerance in construction, but also to allow for this kind of differential movement when they contract and they expand. And this neoprene, no silicone. This is the section, again, the full system. And in this case, they have a full profile. So you will have one element which you can adjust and then fix by points, those panels, right? Top and the bottom. You see again the simplicity of having the same profile, top and bottom. So the number of elements you use is minimum. And some window made of tubes and pipes, which you can look in detail if that inspires you to make your assignment for next week. This is another example. Why do I bring this? This is another patent. He had a lot of them, but this is this small spring on the top, right? Just adjusting the element to the floor and to the ceiling. And this is, of course, adjusting by pressure, giving some kind of elasticity, but having a prevision of the structure, having movements, the slabs coming down, and having that margin for the structure to move. Depending on how we build, and especially if you have steel floors, they are very elastic, they move a lot. You may have going down when it's very loaded, and then going up when it is not unloaded, and that can destroy any kind of joint we have. So this kind of elasticity to have always things tightly connected is a good solution. And this just to give more ideas. See, this is a vertical section. You can see the concrete, one kind of made to order AL element embedded in that concrete. You see the teeth or that kind of a shape, which makes very tightly fixed the following element. It will not move, but see how the hole is longitudinal. You have some margin to adjust in depth the element. The second element, right, has not a small hole, but it's a bit more margin to adjust. If you see from the top, that yellow element will have a hole like this, and then the bolt in the middle with the connection, right? So you can adjust in all that area in depth. And then this connects to another element, which connects the wall, and you have always in between that elastic connection. So nothing is tightly connected to the next element. This is the keyword. And this is quite interesting because the dimensions allow to have the finished floor just horizontal without any kind of opening or height difference, right? The idea is to have maximum simplicity when things are finished. See again in the exterior elements made by pressure, right, with the bolts, but never touching directly the panel itself. Interior corner elements, again with this elastic joint, and always the neoprene gaskets, right? And this is just a specific panel just to solve the interior angle, which is an element we will see very seldom. What you see outside is the folded plate. This is called shaped. You have the roll of the metal, right? You cut what you need, and then you just bend in the shapes you need to make this element with a press. So this is a very easy question, just to have you awake. So we commented that Proove uses one material for sealing the joints, right? The glass, the panels between panels, and I give you 4 choices. Choose one. It is very easy. You follow the lecture. Which is the element Proove uses? Glass between panel and structure. What is that sealing material in Proove's panels? You have 4 choices. We have just 10 seconds to reply. You have only to choose one. Okay, one example coming closer, but okay, Norman Foster is really old guy, so 1979 is quite a long time ago. But Sensory Center is one of the most amazing projects of the early, well, not early, actually it was not so young at the time, but the early Foster, in which he has a very clear structure, right? And an envelope applied to it. So it's like the perfect panel element with very strict modulation for structure and panels. See how the structural elements have already integrated the first element for fixation. And the same solution applies to the roof, which is quite interesting. So the column and the beam are almost identical, at least in the drawings, right? And they all will fix in similar ways. And you will have panels for facade and for the roof. And this is a process for the roof. So see, this is just 2 people outside and 1 inside. And in this case, you see about maybe 15 centimeters thick. Now standards will demand for much more thickness or much more efficient insulation material, right? So just place it, and then you have the gasket still in the connection. And don't ask me if it had leaks or not, because I don't know, but the building is still working, and it's one of the famous elements. So the beauty of this is that the elements are very easy to manipulate, easy to assembly, and you have to make any maintenance. It's very easy to replace or to move them at any moment, which you don't have with that heavy prefabrication. In that case, things are meant to be much more permanent. And this elevation, right? So good design, has good details, and both construction and building has some kind of strength, some kind of personality. And you see that if the solution is correct, there's not any problem of being simple. Right? To design simple things is much, much more difficult than making things very complicated. We see around so many curtain walls with maybe bored architects, which think all the facade is boring. Let's make some diagonals, some cuts, some gesture, which have not any meaning. They only complicate things and don't make the building more beautiful. They make just more complicated without needs. So it's the difference between good design, good architecture, and just, I don't know which word I would use for that, but just that. Okay. Another interesting, again, James Stirling. If you don't know him, it's worth studying. One of the best architects in Europe in the 20th century at all. He died relatively young, but he did one of the few examples we have with the plastic panels in facade. Again, Olivetti Center in Surrey, in Great Britain. It's 1969. This is very interesting case of expansion, actually. It's old building with a glass connection and then the new building expanding outside. Right? It's a very intelligent way of making an extension to one building. And then kind of organic connection, two elements which are totally modular. One special element, which is the multi-purpose exhibition room. And then the soft element is connected is all glass. I don't know if I said, if I did, I repeat, British have a long tradition of greenhouses and in general have very much good hand and good design for glass. Norman Foster, James Stirling, right? James Paxton before, the bow window we saw yesterday with the Voici. The idea of window and glass is they're not the only, but you have always a lot of good examples from the British guys. On this case, let's not go to the full project. Actually, this is quite a nice project for 1969, but you see that it is like basically one piece which is longer and shorter depending on the plan, and then one element which connects to the roof, right? So two kinds of pieces, and then a special for the corners. This is applies as plastic. That's kind of fiber, if I'm not wrong, fiberglass reinforced resin, right? Some kind of resin. See, they very much looks like cars or ships or boats, probably. And it was quite an interesting experiment. He didn't repeat it, but this building was small, but had enough number of units to justify the experiment. And then let's go closer. Also, it is already 10 years ago. Sana, the new Louvre Museum. So when it seems that the prefabrication and that thing is kind of old-fashioned and looks like a really 1960s, 1970s, we have projects which bring kind of new vision to it, right? And Louvre is one of the examples, in which it's just the material and the simplicity, right? Well-chosen material, again, very expensive, very thick, right? So you can have one element, not just the sandwich with many elements there, but which creates some kind of effect which is unique. It's quite contemporary. So we benefit from the experience of people developing those elements before us, but still there's room for creativity without going to those exotic gestures to show genius, right? Again, being simple is one of the keys of the success of the Sana office, right? And there's a lot of work to achieve that simplicity. I don't have the details, so we could have a case study, but we have to go through the lecture with the time we have. Glass only, there are many solutions, and probably the most popular in Korea for some reason became the spiral system, right? But we have also clamp systems, so you can have other ways of doing it. This becomes very common because it is very reasonable and works very well and can be adapted. What is the problem of the glass only facades in general? You have very clean glass outside, you have a mess of a structure inside. You have to deal with wind, all the things that happens inside of the building. So creates fantastic facades if you do well, but very ugly interiors. There's a trade-off there. The problem we have here, this was invented when we used a single glass. If you use a EGU and tempered glass, right? Tempered glass, against the glass reinforced by thermal treatment, you have to have the holes or the perforations made in factory. Right. So you have to be very precise because they have to match the spider, which has some tolerance, but that's not very forgiving. That's the only thing you have to be aware. If there's a mistake, you have to fabricate a new pan of glass. You cannot perforate it. Again, Jean Prouvé, the first one. Right. And in 1971, to have a full facade of only glass was very unique. It was not so much published, right? But I think it's quite a kind of genius. And again, you see the simplicity of the solution. Here, you have to work from the outside. This is one of the problems also with this kind of facades. You need a lot of infrastructure. You have already insulating glass, 1971. The energy problem started in 1973, right? There's the first oil crisis. Before 1973, almost nobody worried about climatization. So it is quite amazing. This guy in a building finished in 1971 already thought on saving energy and having more thermal comfort in the building. But see the simplicity. You have structural standard steel pipe, probably 2 EUs welded together, to which you have a bolt, right? And a clamp. A very simple steel element folded. This may be the 2 millimeter thick element with a bolt, right? So the bolt just pulls the clamp, but you have only neoprene between the clamp and the glass and the structure. And see the shape of the neoprene. This is what we commented on the window the other day. This shape is made to make the neoprene. Let's change the color. Right? So as you press, those elements become tight, right? Pressed, and you have a lot of points of contact and air. If you have just flat neoprene, the irregularities will make probably less safe joint. So this is the meaning also of those kind of strange borders in the window detail we saw yesterday. And only one bolt. It is amazing how simple and how effective it is and how elegant. And this is Prouvé sketches, right? He had not formal training as architect or as engineer, but his mind, his way of working is much better than most architects ever, right? I brought this not only because the sketch is fantastic, it's because detailing is design also. You have to think and find the logic and make it work. The only difference of the detail with the whole building is just the scale, right? But the concept idea, which the logic of the building should show in the last detail. And I think that's something that what Prouvé was very clear. Corner connection, this is a different patent, but again, curiously, this is a single glass with, again, designed on other elements, which were probably insulated with the clamp, right? And the screw, the bolt, which will fix by pressure. In this case, the elements are smaller. Probably here, the question of insulation was not so much a problem. And in this case, you have no choice but to use silicone because you have to stick the glasses. In this case, it is mechanical. In this case, it's just the adherent, the glue. And then just a few years later came Foster. And this was contrary to Prouvé, this was published everywhere. This is already quite prestigious company. This is the UK, right? And they had all the publications in the artisanal market. When they published this building, everyone said, wow, this amazing, looks kind of wavy building. A little bit, the idea of Mies van der Rohe with his glass towers, also in low height, was achieved here for the first time. See how intelligent is Foster. I don't know how on time. Oh my God. not even half the lecture. Okay. He just designed the structure in a way that you have minimum thickness to the facade. So everything looks light, even though you have a very thick structure behind. And then the glass has the clamps, but all the reinforcements needed, all the fins are made of glass also. And this is single layer. Glass, right? See the difference of Prouvé and Foster. This is office building 1975 and still was single layer glass. Prouvé was working with already insulating glass at the time. And of course, this is very expensive stainless steel glass. And quite interesting, but very much more complex design than one of Prouvé. It's not that this is bad. It is just to show the merit of Prouvé inventing things with that simplicity, which in Foster, at least visually, it was simple, but so the clamps are extremely simple, just elements with screws on both sides and elastic joint. But the connection with the rest, as we said, the connection with the parapet, the roof, is always a small complication. And well, when glass break, yeah, people were so happy looking, but you lose the safety, so you have to replace the glass. The point is, being all independent, it doesn't expand to the glasses. So it was sold as one advantage of this system. So the deal of the clamps, again, you put pressure from the inside and outside, and that connects the glass one to another. And the spider system is just the same. This is some random building in Seoul. So you have solutions for almost any kind of connection you need. And the only point is that all joints are relying on the silicon. And it's not a good idea to put in roofs because we have leaks often, as it happens in Hana Square so often, because that's only silicon joints. You have the problem of cleaning. And the problem with the insulating glass is that it's not so clean. So the joints become quite thick, very apparent. And if you have the insulating glass, you have this element which with a sealant element in both sides, right? Then you have the black silicon in between. You have quite thick element in between, which breaks a little bit the simplicity of the only glass facade. So I think that's kind of a weak point of the only glass nowadays. Well, this was a building in construction, so you can apply to almost anywhere, but just the complication even for the construction. And well, this is quite elegant in Tokyo, but you see problems. I don't have detail. I wish I have it because that corner is a nightmare in terms of construction and detailing. And see how you need to apply windows which can be open. Probably this is because of fire protection to let the smoke. But when you have to put something which is operable, this is complicated. And see how this part is a roof with garden, and that joints are so subtle. When you need really insulating glass, things become much, much more heavy and apparent. So surely this is a single layer security glass, and this is insulating glass, and the aspect changes radically. Problems with it. Okay, the thickness of the joint, the structure which is very tight connected, so probably in plan, that column maybe just a few centimeters from the glass. So there's no way to clean inside. They make the finishes probably before they apply the glass. And you have all the structure of the spandrel on site, which is something which is not always nice because you may have suspended ceiling and you see all the dirty things behind. So these are weak points you have always. And then, as we said, you recognize the drawing on the left. Unrecognizable. This was the illustrations which won the competition of Seoul City Hall extension. This was what the architect, Yugol, which actually is talented, okay? He has a good reputation, but this is what was sold. We have a transparent glass connecting to the sky. This is the Citizens Lounge, right? Open, and the metaphor of the happiness, future, openness, and so on. And this is what we have in reality. This is you cannot see the sky actually. Again, I think this is close to Freud, saggy, in terms of design, right? So when you design those things, you have to be very aware of the possibilities of the technology you are using. Probably this would have been possible, but with another technology, right? Maybe more expensive, more difficult to make. And this is one thing I hope we are all very aware of, to visualize, to be aware of the result of whatever we do. So see the difference with Foster, right? In this case, it's only glass, but it's much more simple. It was just filling floor by floor, and was already difficult enough. And it's not only that, this is a huge glass facade only in Tokyo, right? You have also typhoons, as here you had earthquakes. From the outside, it's amazing if you like glass. From the inside, well, it's nice if you like the structures and mechanisms, but probably it's not so great either, right? With more examples, you may have any kind of very expensive gold embodied in glass and work independently of the structure, and so on. Going to another system, I think we will start roofs on Friday next week, not today, but I don't want to run. Okay, this is what we call the unitized system. Right, this one a specific case, and actually it is the case of the light panels we saw before, but it happens with glass. This is like a full box which contains the window, the interior panel, the shading, and you just put it in the building. See the connection system. We have the railing, the first angle, right? So you can have adjustment in depth, and then a second element which is fixed, right? And you can adapt in depth and then on height. So you can adjust on 3 levels. You have intermediate element, right? Very safe, very interesting, because now the trend is to have the connection from the top, so you can work from inside the building. So you have a safety question there, and you have plenty of room for adjusting and quite a large margin. So this allows the workers to put their hand tools on that area, right? This is the K Tower. So it's Renzo Piano. These panels came from Holland, right? It's not Samsung. They were fabricated and shipped from Holland to Korea. So it's how they arrived, and then they are just placed one by one. And the joints again between panels are gaskets, neoprene. And this is the result. So again, very elegant. The panels go top to bottom. They're huge, like 4.5 meters or something like that. That's very high tower, and they work perfectly, right? And the result is very perfect because everything is fabricated to very tight tolerance. So elegant, well-functioning, airtight, insulating. Well, without problems is this, because each element is independent, so you don't have problems of big movement, as it happens with a full curtain wall within one piece, right? But it is very expensive. We have examples of this kind of curtain wall in other places of Seoul, right? But this probably is one of the most special. And then we have the everyday, the cheap one, what we call the stick system, in which you just put the mullions, the spandrels, and then you put the pieces. This is what we see everywhere. And this is the system. So we have the fixation. We don't go to the detail. So nowadays we put on the top, but that's just the concept, right? Elements which fix the mullions are structural. And then to the mullions we fix the spandrels, which is the horizontal elements. You know, the concept of spandrel is the space between floors. So anything which relates to the spandrel is called the spandrel. Spandrel panel, spandrel bar. Some people call this also mullion, right? But to avoid confusion, spandrel bar, it's okay. And then you have a frame to which you apply the glass panels, right? Or solid panels or non-transparent glass in the spandrel area. And you have always that problem of the operable windows, which if you don't have specific solutions, as we saw yesterday, will break the rhythm of the full curtain wall. So that's what we call the system. So we have the anchors to the structure, which already, you know, it's allows for a fixation, but curtain walls may be very high. So they need some kind of a need for expansion, because you will have a full sunshine in summer, plenty of cold in winter, and again, the slab will be always heated with air conditioned, so it will be brutal difference in temperature. So since it's very long, right, very high, you put like a soft connections between mullions. Usually it's like a 1 mullion having kind of space over which the following slides. So that allows for some movement between them. You can do by floors, I never saw it. You can do every 2 floors or 3 floors. So it's not very apparent, but that happens. So they have some margin of movement. They are all fixed, right? But if they expand, they will not push the others. So it will be, that expansion will be limited to the space between joints. So it will be very, very tiny. And you will see them everywhere. So you'll have all the variations. This is the cheap curtain wall. It's very simple. Once you have the frames, you put the glass, and that's it. Why it is so popular? Because one company does the whole envelope. You have to deal with the people making the windows, with the walls, the render, and so on. So even though it's not efficient, it looks cool. You have your glass tower, you have modern building, but actually it's chosen because it's cheap, it is easy, but it's not great in terms of performance. This is the example of Sana. Again, I don't have the details. Probably we could have a case study for this, but it's got really elegant, minimalistic. And then we have the flush glazing. This is a specific case with the mullion system, in which what we saw before, we have the mullion with the space for the glass, right? It could be fixed with a clamp or with whichever system from the outside. If you don't want to have this vision on the outside, what you do is just to stick, literally stick the glass to the mullion. How do you do it? By structural silicone. It's silicone and glue at the same time. They are guaranteed to hold the glass. I'm not happy with it, never tried, but, and then gaskets, right? And you have a gasket and structural silicone. So the glass is literally glued to the structure. You may have also tape, right? This is taken from the Scotch, from Tessa, sorry, from one of the buildings. So what you see is kind of line with double-sided tape, structural double-sided tape. And you can combine both, have a tape, and this is young tape, right? Very strong one. And this is an example of one building with all the panels just stuck to the structure. You have the choice, and you have the reference if you want to look for it. Seoul City Hall is one example of flushed glazing, right? So you have the space to have the triangles embedded. Actually, we have irregular shapes. Triangles are a very intelligent way of doing because you can replicate any kind of a wavy shape. And then we have the super high performance glasses, right? This is a very specific solution. Again, if you want to have a real curtain glass performing well, you need a really specific engineer office dedicated to design only that part, because that becomes very difficult. This is a photo I took in Mackie Associates office. So I visited several times, but one day I came, it was raining, and the Mackie had his office, well, the meeting room, the mock-up. This is like this big. I said, oh, look, Santiago, we are now completing the New York World Trade Center tower. And this is the mock-up of the model we had from the consultants, and blah, 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 blah. So it was raining, so my camera had water on the glass side. It was in there. But you see, this is the exterior side. This is the interior. I think this is another thing, right? So forget about this. You have 4 layers of glass, and there's no silicone. Everything is cut by pressure with this kind of tiny, this kind of brass element by pressure with a gasket in between, right? And they have very sophisticated series of thermal break elements and connections to connect from the outside to the inside. This is all the insulation of the spandrel, right? So the 20 centimeter insulation. And there's the interior finish. Again, you see thermal break 1. Well, I have it actually. I sketched on the one exhibition later. I had more time for that. And I took the approximate dimensions. So it's almost, let's close this. totally 25 centimeters of curtain wall, right? And you have 18 centimeters of insulation plus air chamber and all the elements. So this like, as we said, 1, 2, 3 sites with thermal break. And we are just 5 minutes from the end. And you see, this is so tiny, and this is brass, and the glass is totally in the same plan as the frame. So this is perfect border. So the glass, well, you can see in the photo, the glass is totally in line with this brass element. And this is exact dimension, it's tiny. It's like probably 20 millimeters or so, right? So on the outside, you don't feel it. It looks like a really, really flat glass. And there's not the dirt of the silicon, right? So this is very thick, but this is the closest to the only glass facade. So this is a summary. And we just saw what we see in materials class in 20 minutes. So it's the basic typology and the glass curtain walls, right? One thing, since we have not much time, we cannot go much further. This is a new engineering building, and you see the glasses are very wavy. Right? The reflection is, this is a J-Con, and J-Con, I remember it was straight, right? But you can see it looks like really wavy. And Professor Fabio was very upset. How can they come? This is ugly. Madonna. But that's the problem with glass. So that happens always. So you may make the detail in a way it happens less. But glass is very thin, right? And it's supported on the top, on the bottom, and maybe on the sides, but it is supporting its own weight. So it has some kind of small buckling, right? So it's just about the physics of the glass. And with the thermal movement, they will become more apparent or less. You can make the details so the glass doesn't buckle so much. You can decide the thickness of the glass, you can calculate it, but it's very hard to avoid it. So the trick is to have reflecting glass only where you can reflect the trees, the sky. If you have buildings in front, it will be very apparent things are not flat. So in the case of the World Trade Center, the tower we saw before, well, you reflect the sky, this is perfect, right? But then on the buildings, better don't look much. But what is expensive one? So probably the glass here is not bending so much. But if we go to, for example, Seagram building, which is a very expensive facade, you see the same problem. Not as extreme, but that happens, okay? And we have to finish because we have just 2 minutes. Just to complete the activity sheet, well, just to complete, we have the EFT, the Teflon elements, right? Which is, since this is a membrane, to get rigidity, you have to inflate it. So it's kind of balloon. Quite interesting. It was very well in facilities. It is very safe, elastic, it doesn't burn like other plastics, but it doesn't protect you against noise. So this is a big limitation. And we have an ugly version of that in the City Hall. This is quite interesting, but you can see by the way it's done, this is not nice construction. It's very rough, kind of. When you make this kind of building, you have to do like Foster with these clients, or Sterling with Olivetti, or Ponti with Pirelli, right? Clients which really are committed to make a perfect solution, not to people who want to have the very unique building on a cheap budget. You need some kind of commitment there. But well, this kind of balloon there is this kind of material, the same principle. Again, another drawback, it is very hard to clean. Just to complete the activity, we don't have time to make this, so just I knew, so just write please to practice at home, and please do at home because you will have the oh, let me, yes. So just write this, so I know you were awake and you were listening. Write it, write in the sheet, so I know you were listening in the sheet. To do at home, and this please, when you study this weekend, before you do the assignment of the window, do this at home. We did this, I think, in construction materials, probably. Well, not every year because we usually don't have time, but it's nice reminder. So just choose the materials. Of course, if you look at the book, it is easier. It is better you get the handout when it's published. I will publish today all the videos and the handouts because yesterday I didn't have time. But please don't forget to write this with your own hand, or those online to do in the computer. So I know you were awake 1 minute after the class. Okay, so we had only about 50 slides left. We will see it on Monday. So let's end the class here. And as usual, if you have any kind of question, comment, complaint, suggestion, whatever, please let me know. And as usual, I will try to reply at least by next class. That's it.